everyone. I'd like to welcome you and thank you for coming to this event for the Texas Science Festival. Moonshot Ideas for AI and Robotics in Dementia Prevention and Care. This is a very exciting opportunity for both our centers, the Texas Aging and Longevity Consortium and the Center on Aging and Population Sciences, as well as the Department of Human Development and Family Sciences. This event, we're grateful to all of our sources of support, and we're particularly grateful to our amazing lineup of speakers today. I'm going to begin by just giving you a quick introduction to each of them and let their research speak for itself. Today, we're going to have 4 talks. 3 of them are going to be on robotics, recent robotics and AI, and the technology is going to blow your mind. We're living in science fiction right now. And then we're going to have conversation involving the chair of our neurology department as well as you about what the implications of this technology could be for all of us going forward, and particularly in the areas of aging and dementia. Our speakers will be Dr. Justin Hart, who's an assistant professor of practice in the Department of Computer Science. His work focuses on transforming how robots assist people in everyday life. He co-directs the Living and Working with Robots project and has been recognized by the Society of Manufacturing and Engineers Innovation Watch List for his forward-looking contributions. Dr. Nanshu Liu is a professor in the Department of Aerospace Engineering and Engineering Mechanics. She is an internationally recognized leader in bio-integrated electronics, and you will know what that is after her talk. Her work has appeared in leading journals and has been highlighted in major outlets including CNN, BBC, NPR, and most recently, some of you may have seen the terrific story KXAN ran on her work earlier this week. She has earned major honors, including the NSF Career Award, the MIT Technology Review's 35 Innovators Under 35, and the 3M Non-Tenured Faculty Award. Dr. Joydeep Biswas is an associate professor in the Department of Computer Science, whose leadership of the Autonomous Mobile Robotics Laboratory is advancing the development of robots that assist people by navigating and reliably interacting in real-world human environments. He has been recognized by distinctions such as the NSF Career Award, the JP Morgan Faculty Research Award, and the Amazon Research Award. Finally, our discussant for today is Dr. David Paydarfar, who is the chair of the Department of Neurology at Dell Medical School and director of the Melva Clinic for Neurosciences. His research is personalizing healthcare for individual patients, using sensors and devices and AI to enable doctors to forecast and avert adverse disease trajectories. He's a leading expert in the neurological conditions of late life, to which we will be hopefully applying these technologies. So without further ado, I'm going to turn this over to Justin Hart to tell you about his exciting work.
Yeah, hi, so I'm Justin Hart, and thank you for the introduction. I'll skip telling you who I am. But I work on problems in artificial intelligence and human-robot interaction. And there's been a trend in robotics lately that has made robotics more visible to people. Robots have traditionally thrived in highly structured environments. There have been robots commercially deployed since the 1970s. And the first application of those robots was like these KUKA arms all the way on the left that, unfortunately, my video is not replaying automatically, but KUKA arms all the way on the left, the first video that played, right? They've been working in automotive manufacturing partly because they can kind of work like your 3D printer does. The sensing requirements are very low. There's no artificial intelligence needed to accomplish this. If the robot performs a repeated motion, it's always going to succeed. And then those robots actually work in areas that are sectioned away from people called work cells, and that prevents the robot from needing to safely interact with people. It also prevents people from messing up the robot's environment, right? So because the robot's in a work cell, and it's working on a work piece that is quote-unquote fixtured, it's clamped down, the same motion will always produce the same result if you're like painting a car or performing a weld or something like that. Some of the emerging areas, we have the first thing that people really saw in this area is sort of Amazon adding automation to their fulfillment centers. There are two traditional jobs in these fulfillment centers. There's a person called a picker who takes items off of a shelf, puts them in something that's like a shopping cart, drives it up to another person who's called a packer. The packer packs a cardboard box and then tapes it shut and sends it to FedEx for delivery, right? And then Amazon, one, integrated all their logistics, but two, they bought a company called Kiva Systems that was developed by a professor named Raphael D'Andrea. Instead of having what people were traditionally doing in robotics, which was to have a robot with an arm driving around to the shelves, picking items off the shelves, what they would do is he built this very sturdy base that could lift like maybe 500 pounds, and then it just puts the shelf on top and drives the shelf around. And not only is this great because it automates that job, which is starting to be automated by other outfits, but also it reduces the amount of space that's needed for the shelves because people don't have to go between the shelves just drive next to each other, pack each other up. And so that was like 20 years ago, vintage technology. If we get into the modern applications, Fox Robotics, which just got bought out and operates in Austin, will take palletized cargo off the back of semi-trucks, put them into warehouses. You have Diligent Robotics, which is a UT Austin spinoff, or maybe a Georgia Tech spinoff, depending on who you ask and how you ask. Doing deliveries in hospitals, right? Aiding nurses by requiring them to do fewer fetch tasks and spend more time on care. And then the same sort of delivery from a Willow Garage spinoff called Savioke, which has a robot called the Relay, which does room service. And as you look at this chart, I sort of have these older applications. They're in places with fewer people. You have more control of the setting. You can tell the people are not allowed to walk around the Kiva robots, right? But as you get into like the corridors of a hotel, they're sort of sparsely populated areas, right? Like there will be people in there. If you get into the corridor of a hospital, there's always going to be people there, right? You're moving into areas where there are more people. And sort of the conceit of my laboratory when I started up here is I wanted to build robots that understand and interact well with people. This is what typically would be called human-robot interaction. And robots that operate in places designed for people. And this is a very particular area of artificial intelligence, which is applied to the idea of I'm building AI systems for the purpose of deploying them on robots. This is what people typically think of when they think of RoboCup. RoboCup is a competition. It's run for, almost 30 years now, like 25 years. Joydeep would know. Joydeep would know. 1996, 30. Yeah, 30 with a couple years off. And so when people think of RoboCup, if you're in engineering, if you're in computer science, typically you're thinking of robots playing soccer against each other. But across the competition, I help run a different competition entirely called RoboCup at Home. So RoboCup at Home is all about taking robots and deploying them in domestic environments. And so we take stall furniture, like if you've ever been to a convention, we build something that looks kind of like an apartment. You can see there's like a bedroom back there. This is in the process of being decorated when this picture was taken. You can see that, we have a dishwasher. We can see one of our sponsors, Procter & Gamble, has their logos slapped all over everything. And the tasks are things like answer the door, serve drinks, offer people seats, clean up after meals, put things into the dishwasher. So there are things that are relevant for both making our lives easier at home, but also for possibly if you were an aging person, remaining a little bit more independent. Everyone in RoboCup likes this particular competition, and I'm going to explain why, even though it's a little bit in the weeds for this particular audience, right? Most of the rounds of RoboCup at Home are competed in that apartment area. And the teams are allowed 2 days to thoroughly map the area, to retrain all their neural networks to work in that area, to put semantics down on everything to say, this is the shelf where the food goes and stuff like that, which is relatively difficult to do on the fly. This round, however, we drive off to a restaurant off-site. They're not allowed to map it in advance. They're not allowed to retrain their algorithms or test anything on site. And so everything has to work on the fly in this sort of organic way. And so, yes, there are lots of things that are very funny about robotics at the moment. And probably you noticed how terrible the handover is there. So one thing that is an area of active development is people tend to think that interacting with people would be very easy, that you can kind of design your way around this problem, or you can design your way around artificial intelligence. Or you see ChatGPT and companies promising vision language action models, and they sort of say, oh, well, this is solved. This is not solved. This is far from solved. That's why, yes, when we hand the Bundaberg ginger beer to the robot, people are like putting their hands under it like the robot's going to drop this glass bottle, right? They're very concerned. that could happen, because it would pause our competition, and it's stressful enough as it is, right? But the basic flow of this round is people wave to the robot like this. They're very broad gestures. The robot drives up to them. They place an order. It goes back to an area called the bar and receives items from the bar. We're going to move on, though, because you guys get what this is all about, right? OK. Some of the problems that I work on are very in the weeds, very like pointy end of the stick. How do we make robots interact well with people? And one of the popular problems that has become very popular in human-robot interaction, also very popular at UT Austin, is this social navigation problem. If you think of like autonomous vehicles driving on the road, you can now get in a Waymo, and you can get from one place to another safely, right? And what's dictating the behavior of that robot is the law, is the rules of the road. It's going to signal. It's going to look for other turn signals. It's got models trained on how people drive. When you are walking down a hallway, the name of this video is Awkward Situations, the Hallway Dance, specifically because you are super good at passing people in the hallway. And the incident when you run into someone is memorable because you made an ass of yourself, right? Like this is this easy thing, and suddenly you're having a hard time. But robots have a hard time with that. And so we've done lots of studies where we look at different ways that robots can coordinate their behavior to people. One thing that people were looking at when they were looking at robots like delivery robots is, well, maybe we'll just put turn signals on the robot. And so we actually did an experiment that showed that LED turn signals are not obvious. Like you have years of experience when you were a child riding around in a car seeing the turn signal used, and then being told in your driver's ed class, this is how you use a turn signal. And then when you encounter it in this situation, it's not at all obvious. The robot starts blinking a turn signal when it crosses the black line in that video, or it has a robot face and it looks over to the direction it intends to go when it crosses the black line. You see, the person gets immediately out of the robot's way when it sees the face. The person runs right up to the robot, comes to a safety barrier where the robot was not willing to drive because it doesn't want to run into the person, and then the person goes around the robot in the top video, right? You can also see that the robot's making no attempt to get out of the person's way. When we do these controlled experiments, we're not trying to engineer a product that's like a good to use product, right? We're trying to study, hey, was the signal interpretable by the person, right? And so on purpose, we made it so the robot would run into the person if the person didn't get out of its way. The other question becomes, can we get the robot to get out of the person's way? Can we make it so that we interpret gaze, so we understand what the person's about to do? The robot's producing gaze, and that's understandable. Can we read it? And the answer is yes. Traditional motion capture studies use instrumented motion capture. This is like when you see like Hollywood actors with paint on their face or like retroreflective markers. If you want to track their gaze, you have to buy a special set of cameras that look at the eye, and then you actually have to track those in that tracking cage. And one of the big problems is it's not integrated at all, so your grad students spend a lot of time writing software for that. What I did is I bought an HTC Vive Pro Eye, which is a virtual reality system with an embedded gaze tracker, and that drove the cost down from about $500,000 for that style of setup that I was describing before. This is about $5,000 fully instrumented. The people who wrote the software were undergraduates in my undergraduate program, and yeah, I'm going to speed it up because I know that I have only, there wasn't a sync, but, oh, okay. Don't worry about it, I have track. But anyway, we built a machine learning problem where we said, can we tell where you're about to walk based on where you're looking? The answer is yes. The problem with fielding this on a robot is that there's no technology for tracking your gaze on a mobile robot. There are things out there, people are like, oh, we've got a solution. It is like the coarsest, like you're looking to your left or your right. Like it will give you a number that looks like it knows where you're looking. That number is going to be off by like 5 meters. So it's not yet a trustworthy signal. Yep. So what do? Well, we've all heard of large language models at this point. We're building like a large language model of human motion. We're looking at like how do people coordinate each other's behavior to each other? Can we compute a completion in the same way that if you messed around with large language models, if you messed around with the non-instruct versions of these models, like if you're not chatting with ChatGPT, if you're just saying finish what I'm saying, do that. And then with that short-term prediction, which people do all the time because they're reading each other's body language, can I coordinate to your motion? So I have people doing this in the context of passing each other in the hallway. I have people doing this in the context of handing objects to each other and otherwise coordinating their motion. And then you all have definitely messed with ChatGPT at this point in your life. We have large language model interactions with robots where the robot can write software on the fly, can write Python code on the fly. It can perform different types of interactions. This is a diagram. For time, we'll kind of skip through how it actually works. But we we compared the performance of this robot in a couple different scenarios. The first thing we did with our first paper is we ran tour guide scenarios. This is a classic problem in human-robot interaction. Deploy the robot as a tour guide somewhere, and then you kind of like, spew forth canned text like, we are now standing in front of the Tyrannosaurus at the Museum of Natural History, and it's some kind of horrible monster from billions of years in the past. I don't know. And then, what are you testing? You're testing the mapping capabilities, the navigation capabilities. Here, we wanted to demonstrate that we could have a real-time interaction with the person who's talking back and forth with the robot and show how that improved the interaction. I'm only going to show part of these videos because they're long.
Tell me about the Living with Robots lab.
Okay, I will tell you about Living with Robots lab. The Living with Robots lab, run by Dr. Justin Hart,
so this is the sort of old school way of
HRI.
interacting with one of these robots. And if you go back
Can
even
you
further,
tell me
there's
about
like
the project
a button
they're
on the
working
interface that's like, tell me about this exhibit. On the other hand, you can have much more flexible
Dobby,
interactions now.
I heard you could give me a tour.
Well, butter my circuits and call me a toaster. A voluntary visitor. How delightful. What aspects of robotics pique your interest? We have everything from autonomous vehicles to robot arms.
I'm really interested in human-robot interaction.
Oh, human-robot interaction. The real meet the parents situation for us robots. Would you prefer starting the tour at the Living with Robots lab or the social navigation hallway? Both offer great insight into that field.
So
Let's go to the social navigation.
Oops, come on now. We get some idea how this works and what it does. Part of what we'll show off with this project is that the robot can interact with you while it's doing other tasks. So if you look at like YouTube videos of people like sort of verbally instructing the Tesla robot, go pick up the thing and do whatever, act like a chicken, whatever it is they're telling it to do, right? It does this thing where it's like, take the command, do the action, and then you can place guesses as to how it's generating the action. Certainly people do. But we can take the command, we can interact with you while the robot's performing the task, we can change tracks, we can change what we're doing, you can ask us questions on the fly out of a knowledge base, it all works, right? So people really enjoy that aspect of interacting with this robot. And the only reason this isn't the way that you get tours at Anahist Gymnasium now is that I've drilled into my heads, into the heads of my students that everything they do needs to produce a paper. And I was like, oh, you can do a field robotics paper like this, but they don't see the connection there. They see the connection on like the engineering tasks for the paper. But someone's going to do this paper, and it's going to be great.
Dobby, bring me the food item from the coffee table and hand it back to me.
So this is
All right, let's get this food item party started. I'll head over to the coffee table, grab the food item, and bring it back to you.
so this is all. This is the last one. What this is showing off is, it's clearly a different version of the robot. It's got a UR5 arm on it. It's able to perform manipulations on the fly. But the other thing it can do that makes it very exciting is it's writing software as it goes to solve these tasks. So it has an API that describes the basic capabilities of the robot. Drive here, look for this, find the thing, say what you're about to do, interact with the person. All those things come in a programming interface. But yes, and we've improved that too. But the actual instantiation of all that, the way the robot's kind of thinking, is using the LLM to write a Python script to execute this on the fly while it runs. So that's sort of the latest and greatest. All right, I'm out of time. I've kind of shown off. Thank you all so much.
Good afternoon, everyone. And first of all, thanks, Karen, for bringing us all together in this wonderful event. And I'm very glad to share what my lab does in UT for 15 years now. I actually lost my grandfather to Alzheimer's in 1998. He was super intelligent and deep thinking. However, now there is increasing findings to tell us that actually for those more intellectually active and deep thinking people, the pathology of dementia could develop very early on, but their brains can compensate for their intelligence and recognition such that it's very hard to directly detect their symptoms early on. And because of that, actually, my grandfather, he was like managing a big enterprise, and he was so sharp until just 3 years before he passed away. Actually, after a fall, right after a fall, he passed away. And then we realized actually probably his baseline is already offset a lot that we didn't notice. So that's just my personal story, but as we all know, the dementia crisis is now a growing global emergency. Now we have one new case diagnosed every 3 seconds. Fast forward 20, 30 years, because of the longevity and all, we expect to have more than double of the patients in 2050. And by in just 4 years, actually, compared with 2019, the global cost for dementia care is going to double. And guess who are doing those unpaid care? 70% of the unpaid care is done by women. So then the question is, how can we detect dementia early on, right? It is not easy just because I mentioned the brain compensates itself and can mask the intellectual performance. However, if we can take this multimodal continuous monitoring approach, and by fusing all those data together, we may find traces of early dementia. So for example, in terms of our brain wave, which is called the electroencephalogram, there is a particular signature such as slowing of alpha rhythm or increasing of the theta rhythm. In terms of cardiovascular response, actually reduced heart rate variability, and this abnormal dipping in blood pressure can indicate this cognitive decline. And in terms of the whole body motion, the slowing down of the speed, the smaller swing predicts dementia onset. And if we can monitor those kind of signals in a free-living, natural environment 24/7, right? And then that can reveal a lot of what clinics cannot. And therefore, we advocate for this kind of pervasive monitoring for our seniors and high-risk patients. However, conventional wearables, as we all know, are very rigid and bulky and have limited functionality. That's because silicon wafer-based electronics are intrinsically not compatible with our stretchy and curvilinear and soft human body. So what if we can transform those kind of rigid, bulky electronics to be as thin, as soft as a temporary tattoo sticker that we can slap onto any part of our skin, like the brain, the head, the muscle, the chest, and so on, such that we can have tattoo-like wearables still providing this medical grade data, but in a much more like mechanically imperceptible and user-friendly way. So that's what my group has been working on for quite a few years. Let's see if this can play. Unfortunately, it doesn't play, but it shows you, right? This is the soft, thin e-tattoo that can be conformable to all kind of chest topology, and then we are able to have wireless monitoring of the heartbeat-induced surface vibration. That's called seismocardiogram, as well as the red one, which is the electrocardiogram. And when he starts walking, actually, we also monitor the whole body movement, right? We can tell you the gait and so on. So this was our earliest one that has a dual modality. And this is just validation and showing how low power and small and lightweight it is, benchmarked against the smartwatch in terms of just heart rate. There's no more thing we can get out of the smartwatch. But using trimodal system with ECG, SCG, and PPG, which is the optical signal, we can develop a machine learning algorithm to actually derive those hard to measure parameters like stroke volume index or blood pressure. Right? Otherwise, you have to wear a cuff or an invasive catheter to do that. But this is all mobile, 24-hour, continuous. This is cardiovascular. How about our brain? Well, clinically or non-clinically, it's quite bulky, and Dr. Paydarfar can speak to that. Do e-tattoos work? Yes, if you are willing to shave. So at first, we were not willing to shave, so we only put e-tattoos on the forehead. But we are able to monitor the prefrontal lobe, which is responsible for reasoning, calculation, decision-making, right? All those kind of intellectual mental workload is happening in the prefrontal lobe. So by just monitoring 4 channels on the forehead and ask the subject to do something called NBAC test, we are able to predict and infer the mental workload of the subject. The blue curve is the ground truth, and the red curve is what we can infer out of just forehead e-tattoo. But we're not satisfied that we cannot put tattoos on the hairy scalp. And therefore, we were thinking out of the box. We developed intrinsically electrically conductive inks that can be inkjet printed with very high-speed droplets that can wet and moisten the scalp skin below, covered by the hair. In this way, we have those hair-compatible e-tattoos. We can also brush it on if it's long hair. And we can benchmark against those gold standard. And those conventional shower cap with liquid gel dries after a few hours, and it's no longer usable. But our system can be worn for 24 or 48 hours. And now we have a newer version that is sleep compatible, workout compatible, and we are even developing a fully transparent version that it is not just mechanically imperceptible, but also optically imperceptible. Because it's a tattoo that's so thin, right, you don't nearly see it, it is compatible with any kind of headgear, helmet, hat, VR headset, and so on. Then we can have this immersive environment where you can do a lot of visual, audio stimulations and trainings and rehab work. This is about e-tattoo. I'm just showing you very brief examples. That is for human wear. How about we also leverage the same stretchable electronics technology for robot wear? Why do we need that? Because if we cannot trust a robot to reliably handle a beer right now, do you feel comfortable letting a robot handle your senior or your newborn? That is actually a very difficult problem. That's because robots, they can have like force torque sensors embedded in their joints, but they are still missing this fingertip kind of tactile sensing like human skin, and also like mechanically feeling soft. And this is a very fast developing field right now. And our vision is that leveraging stretchable electronics, we can actually endow future robotic caregivers with a human skin-like softness and a tactile sensation to give us very gentle and intelligent touch. So here we have developed a stretchable e-skin. You can see during the inflation, there is stretching, but there's not much signal. And when it is in contact with human skin, you can see it is only sensitive to the normal force. And even under a large preload, we still have enough resolution to show the surface pulse wave, just like a Chinese medicine doctor who can really digitize our pulse and analyze our diseases. And in the future, we hope to mount this eSkin inflatable balloon on a robotic arm such that we can have now a very safe and gentle high five. We can give you a massage. We are monitoring the forces and pressure all the time in real time, although it's already a very soft balloon. It just feels like human. And it can wipe clean the body. Of course, it can check the blood pressure, but the pulse, but also blood pressure. We're preparing a paper. So with that, I would like to say that my dream is to integrate e-tattoos, which are used to digitize the human body to tell our health status, intentions, and emotions, and e-skins that can be integrated on future caregiving therapeutic robotics, just like the Baymax, such that they not only know our health, our condition, and what treatment we need, they can also provide a human-like touch, rehab therapy, and so on. So with that, I want to acknowledge all my collaborators in UT and across the nation. It is, as you can see, highly interdisciplinary research, including mechanics, materials, electronics, mechanical engineering, and biomedical. And we also thank actually a lot of UT's promotion of our work. And last but not least, I get to talk about all the exciting things, but the hard work is done by my whole group at UT. And of course, we also thank all the funding agencies. Thank you very much for your attention.
All right, thanks everyone for having me. So I'm going to be talking about assistive robots for all. But before I actually get into it, I want to actually explain what I mean by assistive robots. So let me just actually show you first a slide of robots. So on the left are these example robots that we have in my lab. They vary from the cobot up in the top indoors, which can actually move around. It can interact with people and can do many of the things that Justin, for example, showed in his slides. And I'll show you some more examples of such tasks. We also have robots which are autonomous on the urban scale, so they can do things like package delivery in the middle, guide visitors around. And the research that we do is applicable to commercial robots like the Amazon Astro or the Diligent Moxie, which Justin also shared, right? And we want these robots to be deployed in everyday environments, including these urban settings, commercial establishments, and homes. And this involves significant amounts of variability, and the variability is what poses the technical challenges. So when we say robots for all, the for all part implies the robot has to work not in my lab, but in your homes, in the environment that you care about, doing the tasks that you care about, not what I wanted to do, but what you wanted to do, right? So why is this a problem? To understand why this is a problem, let's reduce the robot to its simplest form. This is a robot. A robot does three things. It does sensing, it does planning, and it acts in the world. But the devil, of course, is in the details, and the real challenges is essentially what should it sense? In what representation? Who tells a robot what to pay attention to in the world? If I bring the robot in my environment, what should it pay attention to? If I'm asking it to do something, how does it know what I'm asking it to do it? What should it pay attention to? What should it look back in its history of observations pay attention to? All of these. So these are the big problems, right? So essentially, when you're sensing, what are you sensing? When you come up with a plan, how do you know the plan is something that is actually what you asked it to do, right? So there's a lot of research going on in my lab on how we can build these assistive robots, but I'm going to focus on two questions today, only two questions. So first, what should the robot sense and perceive in the environment, right? And secondly, how can the robot perform arbitrary tasks that the user wanted to do, okay? So the first one, I'm going to answer in the context of urban navigation. So you're in a campus. Let's say you have an assistive robot here. It's maybe delivering a book back to the library. And it hasn't necessarily been on campus very long. And you tell it, like, the library is like roughly that way. You got to find it over there. As a human, we know what to pay attention to, right? We know that when you go around on the road, you got to watch out for the bikes. You got to watch out for the e-scooters and all of these other entities. You got to stay on the sidewalk and not walk on the grass. But who tells these robots, right? There are so many other things to care about. So you have these elevated walkways. You have crosswalks. You have foliage obstruction and curb ramps. And the challenge here is that there is a never-ending list. There will always be one more thing that the robot will have to reason about, right? So how do we actually deal with this problem? So the short solution is that essentially we come up with what's called the structured representation. So we take as input these images and sparse depth, right? They go through what we call a perceptual encoder, and internally we come up with a representation. And this representation, instead of telling the robot what to pay attention to, we tell it what kinds of things to pay attention to. So if you look closely, what's happening in the middle is that there's different layers in that representation, which has things like static features. What parts of the world are static? There's dynamic features, which is what parts of the world are moving. And then the bottom is elevation, which is geometry, right? And this is actually really powerful. At the end of this, the robot can come up with an understanding of where in the world is it dangerous to drive, and where is it okay to drive, right? So the black regions in the image on the right is essentially where it is okay to drive in. And this actually works really well. So using this, we've been able to deploy the robots across campus in a variety of environments. These environments that the robot's actually not been in, and it knows what to pay attention to. You can tell it, like, go there, and it actually, without being told what to pay attention to, it's able to pick up these objects of relevance. This is an even more challenging problem when you want to do arbitrary tasks, and you can ask it to do things like, bring me a folder. So the robot has to then think back and realize, where did it see this thing called folder, right? Or you might ask it, bring me the green folder. Which folder of all of the things that it's seen is actually green and what you're referring to, right? So this question of what to pay attention to and what background relevance to actually pick up on is actually a big open problem, and we have several problems that we're looking at over here, okay? So I wanted to switch gears then to talk about the second kind of task, which is performing open world tasks, right? So these are the kinds of things where you might ask a robot, ask Peter if he's free to meet, and if so, find a vacant conference room. Or check all classrooms to see if any are missing whiteboard erasers, and then tell Luke in supplies how many we need to purchase. Or even ask Zarko whether we have the ingredients for grilled cheese. Come back and tell me what I'm missing. So how does this work? So again, Justin explained some example of this, but I want to dive a little bit deeper into how this works. So the way this works is that we use large language models, which power the interfaces like ChatGPT. But under the hood, what's happening here is that there's a user description of what you want. There's a description of the robot skills, what the robot can and cannot do, right? And there are a few examples of example tasks that the user might have asked for it, and some programs. And at the end of it, the language model comes up with a program, and the program that gets executed. So let me show you what this means to actually execute this. So let's say you ask a robot, find which area in the fine art studio I left my backpack. So the robot writes a program, and it goes out and then explores the environment. So it actually checks the different areas, right? It's going to go down the hallway and check the different areas, and it finally sees this the black backpack there, and it says,
I found your backpack in the fine art studio couch area.
Okay, so in this scenario, it found the black backpack in the correct location in the couch area, right? But in this scenario, what if the robot came back and said, it's not in the fine art studio? So I clearly showed you that it's actually there in the couch area. If it got it wrong, what went wrong? Did the robot not visit all these areas? Did it actually not check for the backpack in every area, right? These are actually the challenges of thinking about what could possibly go wrong. And to give you an example of why this is actually a big open problem, I want to talk a little bit about the challenge of specifications, right? So here's what happened. So we were running this robot, and we had a demo on campus, right? And a visitor came and was interacting with this robot. And they saw, this visitor saw our demo and said, oh, cool, I want to give the robot a task to do. And the And he said, okay, the robot should prevent anyone from taking the elevator. Now, we were thinking, what does correctness even mean for this task, right? So one way of thinking about correctness is the robot should stand someplace where it obstructs the person entering the elevator, right? It needs to stand in the middle of the door, right? Okay, I'm going to show you what the solution looks like. I don't have a video, unfortunately, for this. We didn't think to videotape this, but we did record what the program looked like, right? So I'm going to show you the program, and I'm going to walk through what it actually did. This is the program that it came up with. Essentially, it says, go to the elevator, and if you see a person, tell them that the elevator is broken. Why is this a problem? The reason why this is a problem is because when we were thinking about correctness of this problem, we thought about a particular way of getting it right, and the robot came up with a completely different way of getting it right. And who knows, maybe it was deceptive. It could be a form of robot deception as well. So this is actually a big open problem. How do you actually ensure that the robot does what you want it to do and not just some arbitrary things? This is actually the problem of specifications, and there's a lot to be done in this space. So these are just two problems which we're looking at in my lab, and I'm happy to take questions and talk more about other problems, but I hope that's given you a small glimpse of how we are thinking about building assistive robots for all, and there's more to be done over here, right? Thank you.
Yeah, well, I'm David Paydarfar, and so really I'm going to be speaking from a clinician's point of view and also a researcher who works on sensors and algorithms and so forth. And I think a common theme throughout these three talks is that the revolution has started. I mean, this is really exciting work. From a clinician's point of view, my perception, just seeing patients over and over again, is that research is the embodiment of hope, and that when we can't help our patients, we look to discovery, innovation to instill hope. And it's a way, there are many aspects of this idea of research and innovation. One is that the patient feels like we're on their team. We want to actually discover new things to advance their care. So I think that when I listen to these this amazing work, I think there's hope out there. And that, so let's break it down as a clinician. How does a neurologist think about this? Well, the last speaker discussed the breaking it down to sensors, planning, and then execution. So those elements are really important in robots. And so when I think about it, I think, well, when we're trying to map robotics to dementia, we have to think about it a little bit different, but keeping that sort of algorithm, that planning in mind. And that is, we have to think about early detection. So I'll take a quick poll in the room. How many of you in this room know somebody or have family that have had cognitive challenges or dementia? Okay, I'm including myself. How many of you in this room are worried about your own cognitive destiny? Everybody. We're all worried about it because the number one risk factor for dementia is aging. That's it. It's aging. That is the number one by far, is aging. And so we really need to understand. So early detection is really important. So when I think about sensing in robotics, I'm also thinking about early detection of dementia. And this gets back to the challenge that Dr. Liu mentioned, which is cognitive reserve. You know, we have people who are running big businesses, but their cognitive reserve is shrinking. I am sure they want to know that they are developing the pathology in their brain that is impending dementia if there's a treatment. If somebody told me that I could get a treatment for 1 week and it would extend the period of time that I don't have cognitive impairment, I would do that treatment, right? But right now, those treatments are in the pipeline. They're coming. And it's a very exciting time because we see that those treatments are in the pipeline. There are many forms of treatment which we could discuss for those who are interested, but it really gets to early detection. So sensing, the work that you're doing in robotics is going to impact early detection. And you mentioned early before the talk that there are things about robots that people will use in other ways. And right away, early detection, because everybody in this room almost raised their hand, is we would love to know if we are at risk. And is our cognitive reserve diminishing? And the answer is most of us at a certain age. The answer is yes. It's at different ages, though. When is that occurring? That's actionable if there are treatments. And it's very likely that preventing dementia will require early detection and early intervention. So that's number one. Number two thought, I'm just reflecting, then we'll open it up for questions. The other one is safe living. So for those of you who raised your hand about friends and family who have difficulties, they want to live at home. They want to be independent. They love their home. They love their family. They want to be independent. When their kids and grandkids and friends visit, they want to be able to serve them food. They want to be able to give their hospitality. The number one home breaker for dementia is safety. And so I think the challenge of how to map robotic technology to safe living at home is really important. Now, most engineers, how many in this room are engineering engineers? A lot of engineers. LabVIEW, right? LabVIEW is a very Austin thing, right? LabVIEW, revolutionary. Brought together different instruments together so you could see what's going on with different kinds of equipment. We need something like HealthView, where you could immediately see that your loved one is safe. I mean, that's kind of a robotic thing. I mean, it's an interface, really. We need user interfaces. But I think the work that you're doing can be deployed in that way about safe living and people living longer at home. So that's number two. The third one is a very complicated one, and it comes up right away when you see the talks on robotics, is a very famous challenge in rehabilitation and recovery in medicine is what's called disuse atrophy. So we all know what disuse atrophy is. I have the flu, I'm in bed for a week, and it takes me another week or two to get on my feet. That's called disuse atrophy. I'm not using my body, I'm in bed because I have the flu, and it takes me a week or two to recover because my muscles are not deconditioned. So the question, we know that the brain has the propensity for disuse atrophy. So if you have a robot that's doing a lot of work for you, is that going to result in disuse atrophy and make the condition worse? I mean, paradoxically. So we need to know that. We need to understand that. And then we need robots that will learn to challenge you, but not do it for you. That's a very trick. And I use the analogy, I mentioned it earlier, is if I fracture my leg and they put a cast on, if that cast stays on too long, my bone mass is going to go way down and I'm going to lose a lot of bone mass and my muscles will get atrophied. So rehabilitation medicine has had a revolution where we need casts that are not 100% taking the load off the fracture so that the fracture can heal and the bone mass won't lose. We need robots that don't do all the work for you, but they have to know who you are. So the robot just has to learn who you are. They have to understand where you are and then push you so that you don't have disuse atrophy. We could all use that. Large language models, ChatGPT, it's very useful. I don't know, folks in here are doing vibe coding? Isn't it great? Vibe coding? Awesome. I love it. I really love it. I do it all the time. But I know how to code. But what about the ones who don't know how to code? How are they going to actually solve a problem? So the issue is, can we, if we think of a robot as a cognitive prosthetic, it's really helping you accomplish something. Yeah, I'd love it. I need it myself. But you got to let the person push them too, so that they're not losing that capacity. So those are the three things that come to mind right away. So I thought I'd invite the speakers up for a panel discussion, and Dr. Fingerman as well to lead the QA session.
First, I think we should thank these amazing speakers and David also for this was really a mind-blowing opportunity, I think. Here, I'll let you guys come through so that you can find a couple more seats, and we'll let you come through here. We are going to turn it over. We have a few minutes right now for question and answer, and then we do have a half hour to remain and discuss with our panelists. Let me take questions from the audience, and then, Tori, are you someone monitoring the Zoom for questions too? Okay. We're going to start, though. I see we have a question back there. Do we have, we're going to bring a mic so everyone can hear.
Okay, so the question I have is that we have seen the Waymo cars driving around. Can you tell a little bit about how that works and how we can use it?
Cool. Go for it, Joydeep.
Okay, so my lab is called the Autonomous Mobile Robotics Lab, so autonomy and mobility is very central to what we do. So I can give you a little bit of behind the scenes of how these Waymo cars work. Of course, the full details are a secret. But essentially, what happens here is that they go out and build a map of the city. So if you see that Waymo will only allow you to use the car in certain areas, right? And there's two reasons for that. One is that you need to have a map, and a map needs to be very detailed. It needs to have where are the lanes, where is the curb, how many lanes there are, where are the stop signs, and so on, right? And then the second part of the problem is that they have to go out and test it and make sure that the robot actually works reliably well there. But all the time, they're constantly sensing what's around them. They're seeing where the other vehicles are. They're sensing what the stop signs are. And they're connecting what they're observing to this long horizon plan. You're trying to get from A to B. You first come up with a high-level plan of which roads you will take. And then with the high-level plan and what you're seeing right now, it makes decisions of, okay, so right now I see a car in front of me, so I need to come to a halt. And then it actually progresses in the high-level plan. So this is done in what we call a hierarchical manner. And this is roughly how they work. Now, having given this background, I can also tell you like some of the limitations of this kind of approach, which we're trying to overcome, right? The first part where I said we have to build a complex, detailed map of the environment is extremely tedious. Waymo can do this because they have millions, maybe billions of dollars backing them. You're not going to have that in your backing when you bring a robot to your home. You're not going to spend millions of dollars mapping your home, right? So we need more smarts where we don't need detailed maps of our home. When you enter a new home, people don't give you like, here's a detailed map of exactly the XY locations of your fridge and your door and all. You just figure it out, right? So that's where the frontier is. How do we get to these robots to move around in the world without being told explicitly everything about the world, right? So that's the challenge. Okay.
Thank you.
I'm going to give a comment for the Waymo. One is sort of a tangent, but in terms of how good they are, I ride the bus to work and I sit up front and chat with the bus driver. And one day he was complaining that the drivers are getting worse and worse. He's like, the only one on the road that really does it right anymore is the Waymos. So they're well programmed. But the other thing from the point of view of dementia and application, that is the one that I find really the most compelling and the most ready, is that one of the first things that goes, I mean, this is why we see the silver alerts, is you can still drive, but you lose the ability to know where you are. And if you could, and getting mom to give up the keys is one of the sort of interpersonal issues that we struggle with. If we could get more people, I mean, I joke about that I want one of those as I grow older. I'm not just going to call one, I'm going to have one so that I don't have to drive anymore or remember. Or, you know, and again, we could do what David was talking about. Family could have a program too, so that you can't program it to go to your sister's in Florida when your sister is no longer living there or whatever, right? There's an override or something. Yeah. I don't know if you see tremendous, am I fantasizing, or is this...
No, I think this is absolutely right. I think David raised a very interesting point, which I will bring back related to this, which is that as we start using technology, human behaviors, long-term behaviors change. And I think we still don't fully understand how these long-term behaviors are going to change and which of them are going to be beneficial and which ones are not, which ones should we promote, which ones we should not promote. A topic that we've been discussing with a big group at UT and elsewhere is what we call co-adaptation. How do humans and technology reciprocally co-adapt to each other? Coming back to the topic that David raised, there's this term cognitive offloading. So once you have technology which you start relying, you don't think about it anymore. An example is that how often do people remember phone numbers? Nobody remembers phone numbers anymore because we assume our cell phone has it. Who remembers the full names of websites? We don't, because we just type in a rough name and bam, it remembers it. So here's the thing that we don't understand. In a world where we have autonomous cars everywhere and robots which can move around and pick things for us all the time, are we going to be relegating embodied actions entirely to the robots? How will it change our behaviors? Maybe some of them will be beneficial. So, you know, my wife and I, we have a mnemonic that the glass that's over here on the counter is mine and the glass that's there is yours. But if a robot knows where my glass is, maybe I don't need to have a mnemonic. Maybe it'll just figure it out if I just tell, bring me my glass. And I think understanding how human behaviors will change is completely unknown, where it remains to be seen.
Yeah, no, that's a great point. And before we take the next question, but David, do you want to comment on that? Do you think there's going to be a depletion of cognitive reserve if we have the robot doing everything for us?
I personally don't. I think this is a really exciting, I'm incredibly optimistic. And I think that cognitive functions in general, all the ones that I know about, are in hierarchies. And so if you let's say you want to learn to play the piano and you're starting, you got to really be thinking about every keystroke, at a time, and then you start getting pattern. And the engrams, these are called engrams. They get into the brain, and then you start thinking about other higher order aspects of the score, the musical score, and then you start appreciating higher and higher. I think that when the brain loses function, if you can shortcut and get some aspects that are in the lower order so you don't have to worry about it. I mean, I learned programming with machine learning. I would go in and do actual programming in the chips. I can't remember how to do that anymore, but I can still program. So I personally think the hierarchical nature of the brain, it's just the way the brain is designed, is such that as you invent new ways to offload, as you said, cognitive offload, I don't think that will cause disuse atrophy, the thing I'm worried about. But I do worry that as people lose, as they develop dementia, that if you offload everything because you're an overly caring family member, it will accelerate their demise. And so there is something about pushing people to their limit. And wherever they are, you have to meet them wherever they are. And just, so the robots need to learn what that limit is and push them. So that if, let's say we talked about making an omelet, okay? So let's say my mother loves making an omelet and she starts losing that ability. And then you came to me and said, I've got this robot that can make an omelet for your mom. It would probably make her very happy, okay? But probably what's really best for her is a robot that will help her make the omelet, but will push her to regain or really stay as proficient as possible for as long, but she can still complete it, complete the task, give her that satisfaction, but not do it for her. But the robot has to learn where she is. That's the part that's really interesting.
Agreed. And it's individual to each person. I think what each of us find enjoyable is different, right? And understanding that is a big challenge.
I had a patient actually a while ago who had terrible memory difficulties, but over many visits, I learned that what would bring back the memories was associating the smell, the scent of like she went on a hike in the mountains and she had completely forgotten. Her husband was with her once. And then just randomly, he mentioned, don't you remember that we found those wild roses? And then she remembered the whole thing. And so the robot needs to figure that out. Like, it's the sense of, that's one sense.
Yes.
And it'll cascade into functionality. But if you just take it over completely, then I think it'll worsen the dementia.
This is an interesting line with regard to individualizing. And let me get the next question. We have a question here. Sure, we'll take Heather and then we'll come up forward.
So you're saying, we need to challenge somebody to the capacity of their limits, and the robots need to learn the limits. We as caretakers need to learn the limits. Do you think that robots may be better able to evaluate somebody's limits without the emotional and subjective components?
That's a loaded question. I personally believe that there are examples where that could be similar to the Waymo is more safe than some of the other drivers. Yeah. That it may well be that the overly doting caregiver who cares too much is because of emotional reasons, almost like raising children or how people treat their pets, or it's just human nature. And so it may well be that there are many examples of what you said could be true, and that a robot would do a better job.
I don't.
All the other robots.
Yeah.
So So one of the big challenges in the area that I work in is that it's very hard to model human behavior down to like the level that you can describe it with an algorithm, machine learning, right? If you read like a psychology book, it might say something like, you know, a person looks where they're about to walk, or maybe it'll say like, you know, someone blushes when they're shy, right? But measuring that in real time with the robot and actually seeing that is an entirely different problem, right? Like, yes, you could engineer a sensor if you know exactly what you're looking for, but often we don't know what we're looking for down to like the microscopic level, right? Interpreting point gestures is an open thing. Knowing when and how to communicate is an open thing. Large language models sort of emulate that, but they're not modeling like underlying thought patterns. You can kind of extract something that looks kind of correct, right? Like, it's the very misleading thing about the technology at the moment, is you can generate good-looking output. That good-looking output is not grounded in anything that's useful, right? So in my area, you know, what we do try to do is to build those models, and we're making rapid progress, just not as rapid as people may think when they look at all these demos. You know, there is an active area of human-robot interaction, which is monitoring these behaviors. You know, what are the levels that we can do that at? Right now, the demos are like, you forgot to take your medication today because I didn't see the medication bottle move, right? In the future, yeah, probably the robots can do a better job, not just because of emotional detachment from the subject, but because you can watch the behavior all the time, right? Nanshu was talking about noticing differences in your gait and things like that, right? But if you look at how we conceptualize how people can think and how they communicate, one of the things that we look at is sort of like theory of mind modeling. You know, I have a certain set of facts in my head, you have a certain set of facts in your head. The motivation to communicate comes from me wanting to put facts into your head or get facts out of your head that are relevant to me. You know, did you put the keys on the whatever? If I didn't see that, then I ask you, right? Right now, where we're at is that in very structured environments with very structured inputs, we can do that. In free environments, you know, where anything can happen, we can't accomplish that, right? However, if we're able to accomplish that, if we're able to break down all these communication primitives, if we're able to break down your behavior and model it, we'll be able to catalog it and log it in the same way that you could catalog and log failures on a computer, right? We'll be able to diagnose things because we'll be able to pick out facts in the same way as you could out of those logs. All the technology at the moment implies that we're actually capable of doing that, and that's an engineering challenge. Right now, it's a science challenge. Right now, that is sort of far in the future. It will require a lot of work in the area of human-robot interaction and in those types of perception. But you know, it's totally feasible. It's totally feasible once we get over those technological hurdles for the computer to do a better job.
This is a good point that I think all around one of the sort of hidden messages is that no, robots are not going to replace us. Robots are a supplement, robots are going to be helpful, but there's a degree, at least not in the immediate future, there's a degree of individual need and of emotional need that as close as we can get, we're still going to need humans, and we're still going to need humans for certain tasks as well.
Just to throw it out there, you know, the people who are saying that robots are going to replace us in the very near future have a very high economic motive for you to believe that, yes, right? Yes. And they have a very high economic motive for themselves to believe it, right? You know, there are a lot of companies out there that are taking a lot of money. I don't want to say bad things about those companies because I want them to give me money, right? But, you know, and because I like the people who are involved in them, you know, these are friends of mine, right? You know, like, but I would say that, you know, the way that they're treating these problems right now is if you look at like a vision language action model, like a VLA, right? What's an appealing pitch for that? And, you know, we were talking about startups, we were talking about, you know, how you fund these things earlier. There's like, you know, there's the total world market, there's the total addressable market for your product. This is how you evaluate your company, right? If you're pitching a vision language action model, if you're pitching a VLA, you say transformers exist, diffusion models exist, I can train these things. And if I have the single missing piece, that's the actions, because the language came from the internet, the vision came from the internet, we have a big data source. I can provide you with the data source. I can provide you with, you know, thousands of hours of people welding things because I run a factory where people weld, where I can instrument that with cameras, or I can do this, right? As a startup pitch, that's great, right? Because you can identify the market, you can identify who will purchase it, and you can identify the source of the data. There is a problem though. You can't identify how you're going to model the action space in a way that like works, right? So you can identify the problem, you can identify who will buy it, which you haven't identified is that there's like a technical advancement that you may need, right? You sort of have it because you can sort of show it in the small. You can sort of show it working on a limited data set. We haven't shown like super general. That's sort of the big leap. That might be in the weeds, but like, yeah.
Yeah, there's still a leap that we need to take.
There are technological leaps to get there.
We have another question here.
Hi, everyone. My name is Kennedy Shorter. I'm a recent political science graduate with an AI governance interest. I currently work at the Population Research Center as a research associate. And I do have a question kind of for Dr. Liu specifically, but please feel free to all chime in. I was curious, has there been any steps to take place if these early AI detection models are able to widen the inequality gap in terms of cost and resources? Is there anything to make sure that these early detections will be accessible for all? Because if I'm not mistaken, I just researched like around 45% of dementia patients do fall into the low income category. So I'm kind of curious on, has there been any measures to make sure that this is accessible for all?
Yeah, that's a great question. And currently, what AI is hungry for is data. The reason the large language model is so successful is because it is built on all human literature and all the Facebook, X, Reddit forums. And that's how big of a data pool we use to train the large language model. But if we are thinking about future like a large health model or like a large aging care model, then that means we need those kind of video, audio, physiological data that can be used to train those AI in the future. And currently, there are a lot of like bedside patient monitor data, right, for like patients actually in hospital, but we still lack the capability of collecting like very longitudinal time-resolved natural living data from like when they are healthy to like things start to deteriorate to like they actually fall or get lost, right? So that kind of progressive history currently is like very episodically monitored. So that's why we want to develop those very low cost, accessible, and disposable, comfortable to use sensors. And also a similar thing for the caregiving robots. Currently, like our speakers mentioned, there are already a lot of computer vision data, a lot of audio data as well. However, and they are very good at like factory assembly kind of work. When you only need to control their kinetics, they work great. But when it comes to this very fine-grained, dexterous manipulation of soft objects, or like our wash the fruits, or it comes to like human body manipulation of assistive tasks, then they almost don't have those kind of digitized touch data like human. So we're also talking to a lot of like a big tech, like everyone is asking us, oh, can you make your e-skin as a glove so that we can put it on human? Like a human therapist, human caregivers, nurses, so that we can digitize and collect that data.
That's interesting. So that's how you collect the data to do the
training.
I'm going to ask, I guess, well, let me take one more from the crowd, and then I do sort of have a question for, can we?
Thanks. So we've been looking at the question of finding the right level of assistance, right? And it occurs to me that a very similar question occurs in education, right? So when you're teaching, let's say, a child to read, you also want to find the right level of assistance, right? Except maybe the trajectories are going in the opposite direction. So I don't know, maybe you can find some inspiration from the work on AI in education and adapt it somehow.
Yeah, I can talk to that a little bit because we've been So, with the rise of these vibe coding tools, as David was talking about, it's really thrown us for a toss as to what we do in the intro computer science education, not to say of the other fields as well, right? And
just for the audience, the vibe coding is that the ChatGPT can give you computer code so that the intro person doesn't have to learn the code.
Yes, thanks for explaining. So it's essentially the vibe coding idea here is that you just explain in English what you want, and this thing writes programs in whatever language, computer language you want it to do. And miraculously, it kind of just works. And even better, there are these tools which will write code, try it out, see what happens, find the errors, and revise. They're incredible. However, this raises a problem of how do we actually do education in the presence of these tools. So the short answer is that we don't know, but the longer answer is that here are some ideas which might work. So first of all, we cannot pretend that these tools don't exist. Telling people do not ever use these tools is not really a realistic solution. So I think the question is how can we build expertise in understanding the capabilities and limitations of these tools and have constant vigilance? This is actually similar to how you might operate in an autonomous vehicle. Even though you've relegated autonomy to the vehicle, the level of technology today is that you can't fully trust it in all scenarios. You have to be prepared to take over. And there have been plenty of studies which show that if you fall into a sense of state where you believe like the technology is fully capable, you stop paying attention, and that can be really dangerous. So what does this mean for education, and what does it mean for having the right level of assistance? So first of all, we're thinking of having maybe when you're learning how to use these tools in a classroom, you don't necessarily want to start off with the most capable systems. You want to start off with systems which are less capable, so you're forced to be more vigilant. There's something to be said about the system's capabilities roughly matching your capability so that you are on equal footing, right, when you're learning, right? So coming back to this notion of right level of abstraction, one way you could do this, and we're thinking of this from education, is that you can have a very capable system, but you can artificially reduce certain capabilities such that it has the right interfaces. An example for that in a classroom setting is that let's say you have a very complex programming language, has thousands of features. As a new student, you won't know how to use any of them. So guess what? We disable them, right? And then we start with the very simple things. When you develop mastery over them, then you develop the more capable ones. So in a robotic setting, it might boil down to you can do everything, but you have to understand which capabilities you should hold back on, which capabilities you should offer. And this is a personalization thing, and it's a very multi-dimensional thing. There are many factors to account for. So these are just some thoughts, and it's a great connection that Erez for raising the education and customization.
I'm going to build on that just a little bit because, David, you do personalization is one of your research areas. Do you see an interface there? How far along are we in sort of personalized medicine in that regard, or personalized intervention?
Yeah, I mean, I think, in fact, personalized medicine is sort of the origins of the clinical method. So the founders of medical education really emphasized the importance of the clinical method, which is getting to know your patient by their history, their physical examination, and classifying their condition based on the history and their exam, not just thinking about the population at large. You have to be knowledgeable about the population. You have to know everything about diseases, but the clinical method is, by definition, every patient's different. And the example I gave about the sense of smell triggering amazing memory capabilities in someone who was otherwise diagnosed as having dementia. These examples, hearing, for example, hearing's another one where the hearing aid battery goes out and then suddenly it appears that their memory function has been. So there are many, many aspects to this personalization point that you're making. And it also is very important when it comes to how do we want to support people who are sort of the mirror image of the education comparison of learning something new. They're losing capacity, but we want them to be happy, healthy, and highly functional at home as long as possible. And so I think it's a very similar point, is that you just have to know the patient. Yeah, there's so many different models And so this gets to a very exciting area of computational studies that is, UT Austin is one of the pioneers, which is the digital twin technology. And the digital twin technology is different from just simulation or making an algorithm. The digital twin technology is that you are continuously updating the model and you're generating thousands of possible models and finding the best one. And so if you watch the weather report where they have those maps of the weather patterns and the formation of tornadoes and hurricanes, you are watching digital twin technology, because the meteorologists who are generating the digital twin of the weather and trying to forecast when is this hurricane going to hit, where is it going to hit, and how bad is it going to be. But the swirling weather pattern is way out in the Caribbean area, and they're trying to forecast and trying to make a decision about what to do. They're generating millions of models of that tornado, millions. And the sensors, this gets back to the paradigm that you put up on the slide of a robot. The sensors are satellite images, temperature of the ocean and the weather, and it's all feeding into trying to forecast one individual hurricane. And that gets back to personalized medicine. And the digital twin technology now is really taking off in healthcare. And it's turning out that we can do better. This gets back to your question in the back about doing better than the caregiver. So if you think about it, when somebody's going into the emergency room physician is getting multiple streams of data simultaneously and has to make life and death decisions very quickly. They're making a lot of mistakes. Not because they're not intelligent, they're very intelligent, but it's just too much. And so this is where digital twins will really make a difference. This gets back to safety, the safety thing I made, about how do you keep someone safe at home? Well, we have trouble keeping safe at home even when we have fire alarms and everything. Yeah. And I think the robot technology will revolutionize safety. I can see that already.
Yeah, that's an interesting point. So if we have this technology that you can put all of these factors in about the individual, make some prediction, and then maybe have the technology fine-tuned. I mean, this was a moonshot idea. This is not here today. This is how we can put things together tomorrow to solve these problems. I think we have time for another question from the audience, if we have one. Okay, you want to ask it, Tori, on behalf of Zoom?
Yeah, in the chat box. Namki's curious how robotics can help with social isolation and loneliness in older adulthood, and that's with or without dementia.
Yeah, I can mess with this. I can give a good example, actually, from a colleague who Joydeep Biswas and I have been working with a lot lately, Salim Sabanovic over at Indiana State. There's a robot called a Paro, right? It is a robot seal. And what's the choice of, what drives the choice of a robot seal? You may have, when you were younger, owned a dog, and you have some expectation of what interacting with the dog is like, right? And now you're aging, you're no longer able to care for a dog, but you want a cuddly little companion that sits in your lap while you watch TV like your dog did, right? And so, yeah, this Paro thing, right? You have no expectations of what seal behavior is like. The thing sits there, it's warm, it cuddles in your lap, it makes you feel accompanied. You could take kind of a dark view of this, right? You could say, hey, this is a great way to throw away people, because now you have a pet that they can't harm, and there's no reason to have human interaction. The fact that their friends and family don't visit just doesn't matter, right? And that's how I treated Paro for 15 years of its existence, is I don't have anything to do with this because it's a tool for throwing away people. I always offered a counterexample that plenty of people found shocking, but I'm just going to throw it out there. Tinder for old people, just boom, just do that, right? But Salma showed a talk. She gave a talk where she was showing her usage of Paro, and what they had encoded was the Paro would be there, but you would sit a group of people together, and the Paro would administrate a game or an interaction or a group interaction, right? So the way that you do this is you make what the robot's doing pro-social, right? If it is a replacement for human interaction, it's going to let you down in all the ways that you expect. And even if we make the technology better, you're just removing people from the scene. You know, maybe you trick them into thinking that they're interacting with an interaction partner. But you know, the overall social impact of that is probably going to be pretty bad. It's going to isolate people more, even if they may temporarily feel like they're not being isolated, right? But if you can engineer in the things that you want, which is the pro-sociality, which is the thing of like, this thing is motivating you to come out and do the thing. It brings you out to game night. It brings you out to the interactions with the other people, you know, then you can make it pretty good. So the key is to make it unlock that interaction. That's the thing that is actually missing.
So give a slightly more positive take on it, maybe. I would say that there exists a whole field of socially assistive robots, and there have been studies, including your advisor, right?
Yes.
Brand Scazzolati did this work with autism spectrum disorders with keep-on robots, and they have shown clinically that they do actually have a big positive impact on this. So it is definitely a hot area of research. There's a lot more to be done, but there's definitely it's definitely within the scope of things being done.
Why don't I jump down that a little bit, because I was involved in that work, and yeah, I have a soapbox that's like, do it my way. But you know, so Scaz has some very well received work. It was from a large consortium of universities that received an NSF expedition, which is like the second largest grant program that NSF can have. They built a series of robots. The robots that they gave out to homes were these Dragon bots. It was a custom robot. Designed at the MIT Media Lab by Cynthia Brazil's group. We built like maybe 50 of these. And what the Dragon bot came with, and I think that this still speaks to the point that I was driving at, is it delivers interventions for autism spectrum disorders, right? So you could picture that there's like, you know, I never had treatments for autism, but I had speech pathology when I was a kid. You know, you go and you get the kid to say the word 1,000 times, right? And the autism thing, the exercise is more like, hey, like Timmy wants to share the thing, and how do we turn take when we're in the sandbox, right? And so you can picture a caregiver who's doing this for an hour for one day a week, because that's the availability of the therapist. Or you could say that daily, you're going to have 2 hours of exercises with this Dragon bot, and it's going to have games embedded in it, so the kid's more motivated to interact with it. It's unique items, so they're excited about it, right? The robot itself will behave in socially appropriate ways while it's activated. And so the question becomes, does that skill transfer? Like, they can play the game, and they play the game where they exhibit the social skill. Does that transfer to the real world when they're away from the Dragon bot? What they showed that, you know, got them a Nature paper is yes, that it transferred. That like, not only were they able to deliver the intervention and the kid could play the game well, that was already known. Not only did they like the robot more, that was already known. It was already known that children with autism like interacting with the robot. But the idea that this transfers and improves their social skills, that was what was established. So yeah, you could definitely have something like a socially assisted device. Other things that you could do is you could have things like, I don't know, maybe I'm trailing on for too long in my description of this thing, right? You know, and if I am, I could probably have glasses, you know, like Facebook glasses that say, shut up, Justin, it's time to move on, right? So there you go.
That's great. Nanshu, I wonder if you've been the one who's been working the most on making robots less robotic and more human, you know, which is something I have to say, I've talked with Nanshu before, and I never thought about it, that robots are not like these safe little things. They're kind of metallic and big and rough and, you know, not... Machine. Yeah, they're machines. You don't really want them to take care of your baby or someone who's at, you know, risk. So I don't know how you see what you're doing as fitting into the social world, or if you have something more to comment as well.
Yeah, just a very quick comment that actually physical touch, paddling, hugging are making a great difference for those isolated elderlies. And if future robots can give us very soft warmth, hugging and touching, that is going to be a big game changer.
Let me just ask our panelists if you have any closing words or anything more that you'd like to add.
That's great. Thank you.
If we're Well, I do have to say I'm really grateful to the panelists. I think they've shown us where the present is, where the future could go, and what the limits and questions are that we still need to ask. And hopefully, some of us said we were hesitant or worried, but hopefully what we've got going is going to tell us early and help us if we get there. And I'm just grateful to all of you for the work you're doing and to the audience for coming today. Thank you so much.